There is a battery sitting in a lab in Beijing right now that is smaller than a shirt button, runs on nuclear energy, and will still be generating electricity in the year 2075 without ever being plugged in. The material powering it is radioactive. The radiation it produces is so weak that a single sheet of aluminum stops it completely. And when the radioactive fuel inside finally finishes its job 50 years from now, what it leaves behind is not nuclear waste. It leaves behind copper. Plain, inert, recyclable copper. The company that built it is called Betavolt. They are based in Beijing. They announced the product in January 2024, called it the BV100, and as of early 2025, it has entered mass production. Smash that like button and subscribe, because the tech shifts we cover on this channel are the ones most people find out about after the fact, and this one is very much still early. Today we are going to walk through what this battery actually is, why the technology behind it sat dormant for decades before a Chinese company cracked the production problem, what it changes for the industries that run on power, and why the word nuclear in this context means something almost completely opposite to what you are probably picturing right now. The thing everybody gets wrong about charging. Before we get into the battery itself, let's talk about the problem it is trying to solve. Because the problem goes deeper than most people realize. Every lithium-ion battery you have ever owned, in your phone, your laptop, your wireless earbuds, your electric toothbrush, your car if it is electric, runs on the same fundamental principle. Two electrodes, a positive and a negative, separated by a chemical electrolyte. When the battery charges, ions move one direction. When it discharges, they move back. Repeat that process enough times and the electrodes gradually break down, the electrolyte degrades, and the battery loses its ability to hold a charge. This is not a manufacturing defect. This is chemistry doing what chemistry does. There is no version of an electrochemical battery that does not age, and no amount of engineering refinement can fully escape that constraint because the constraint is built into the process itself. The typical smartphone battery holds about 80% of its original capacity after 500 charge cycles, which for most people is somewhere between 1 and 2 years. An electric vehicle battery is far more carefully managed, with sophisticated thermal controls and charge limiting that slow the degradation significantly, but even the best EV batteries lose meaningful capacity over a decade, and when they eventually need replacing, the bill can sit anywhere between $10,000 and $20,000. The other dimension of this problem that rarely gets discussed is geography. Billions of devices in the world are deployed in locations where plugging them in is either impossible or so expensive that the operational cost destroys the economics of using them. Remote environmental sensors on mountaintops, pipeline monitoring equipment buried underground, oceanographic instruments tethered to the seafloor, wildlife tracking tags on animals migrating across continents. Every one of those devices is either hardwired to a power source, equipped with a solar panel that fails when the sun does not cooperate, or running on a battery that a technician has to physically travel to replace on a schedule. In some of those environments, the cost of the battery replacement trip is 5 or 10 times the cost of the device itself. The battery has been the weak link in remote technology for as long as remote technology has existed, and nobody has fundamentally solved it. What Betavolt built is not an improvement on the battery you already know. It is a different answer to the same question, where this technology actually came from. The idea of generating electricity from radioactive decay is older than the transistor. Henry Moseley demonstrated in 1913 that charged particle radiation could produce a current, and through the 1950s, research teams at ARCA in America were building working prototypes they called atomic batteries, devices that extracted a small electrical current from radioactive decay without any moving parts, any combustion, or any heat exchange. In 1961, NASA took that concept to space aboard the Transit 4A satellite, and the radioisotope thermoelectric generator, which converts the heat produced by radioactive decay into electricity through thermoelectric elements, became the power source that made deep space exploration possible in a way solar panels never could. The Voyager probes, launched in 1977 and now the most distant human-made objects in existence at over 24 billion kilometers from Earth, are still transmitting scientific data today, powered by those same radioisotope generators. Across 27 consecutive NASA missions using this technology, not one of those generators has ever failed in service. In 1970, the same principle found its way into medicine when Medtronic and Alcatel implanted the first nuclear-powered pacemaker into a human patient. 139 of those devices were implanted across the 1970s and into the 1980s, and their plutonium-238 power sources were expected to outlast the patients who received them. Some of those nuclear pacemakers are still functioning today, more than 50 years after implantation. The reason this technology did not take over the battery market in the 1980s comes down to three things. The radioactive materials that made the NASA RTGs powerful were primarily plutonium-238, one of the most tightly controlled substances on the planet. Expensive to produce and subject to regulations that made civilian use essentially impossible. The devices ran hot because converting heat into electricity requires a heat source, and managing that heat added size and complexity. And the conversion efficiency was low enough that you needed a substantial amount of radioactive fuel to get a useful power output, which meant the devices were large and heavy by consumer electronics standards. Lithium-ion batteries arrived in the early 1990s, were cheaper, safer, lighter, and good enough for almost every application anyone could think of, and nuclear batteries retreated to the specialized corners of aerospace and defense where their unique longevity justified the cost and complexity. The research did not stop. In 2018, a team in Russia produced a prototype beta-voltaic cell using a 2-micron thick sheet of nickel-63 sandwiched between 10-micron diamond semiconductor layers and demonstrated it could generate electricity from decay without heat, without bulk, and with no external radiation. That prototype proved the concept worked at the scale required for a miniaturized consumer device. What it could not do was find a way into mass production, because the diamond semiconductor manufacturing capability required to make it a real product did not exist in the form that production demands. That is the gap Betavolt closed. Beta-voltaic technology is the specific branch of nuclear battery design that the BV100 uses, and the reason it is different from the RIGI approach NASA relies on comes down to what part of the radioactive decay process you are capturing. When certain radioactive isotopes decay, they release beta particles, which are simply electrons moving at high speed. Those electrons carry energy, and if you can intercept them with the right material before they slow down and dissipate as heat, you can convert that kinetic energy into an electrical current. The device that does this interception is a semiconductor, and the way it works has a close analogy in solar technology. A solar panel generates electricity because photons from the sun knock electrons loose from atoms in the silicon material, creating what engineers call electron-hole pairs. And the structure of the panel is designed to keep those pairs separated, so the electrons flow through a circuit as useful current rather than recombining immediately. A beta-voltaic cell does the same thing with beta particles instead of photons. The radioactive source fires electrons at the semiconductor. The semiconductor's electrons get knocked loose, the pairs separate, and current flows. The challenge that limited this approach for decades is that conventional silicon semiconductors, the material inside every computer chip and solar panel in existence, take damage from repeated particle bombardment. Over time, the crystal structure of the silicon gets disrupted, conversion efficiency falls, and the battery degrades. The solution Betavolt landed on is diamond. Diamond belongs to a class called ultra-wide bandgap semiconductors, and its properties for this specific application are significantly better than silicon in every relevant dimension. It resists radiation damage far more effectively because its atomic structure is more tightly bonded. It can capture a broader energy range of incoming beta particles. It conducts heat away from the device better than almost any other material. And the specific crystal structure of lab-grown diamond can be engineered at the 10-micron thickness the design requires. The problem that kept diamond beta-voltaics in laboratories for years was producing large-area single-crystal diamond semiconductor material with consistent enough quality to build a manufacturable product. Betavolt's CEO Zhang Wei has said publicly that his company is currently the only organization in the world capable of producing large-sized diamond diamond semiconductor material at the specifications the BV100 requires. Whether that exclusivity holds as other organizations ramp their own programs remains to be seen, but it is the specific capability that allowed Betavolt to go from a 2018 Russian laboratory result to a Chinese mass production announcement in approximately 5 years. What the BV100 actually is. The physical structure of the BV100 is almost deceptively simple. A sheet of nickel-63 isotope, 2 microns thick, sits between two diamond semiconductor converters, each 10 microns thick. That layered assembly is sealed into a module measuring 15 by 15 by 5 millimeters, which is smaller than the 5 Jiao coin used in everyday transactions in China. It weighs almost nothing. It generates 100 microwatts of power at a voltage of 3 volts continuously for 50 years. 100 microwatts is a small number. A standard LED uses between 5 and 20 milliwatts, which is 50 to 200 times more than a single BV100 module can provide. And the gap between that and the roughly 5 watts a modern smartphone requires at idle is enormous. Betavolt's answer to the power gap is modularity. The BV100 is designed to be stacked in series to increase voltage and in parallel to increase current, combining as many units as an application requires to reach whatever output the device needs. The company has been explicit that the architecture is intentionally scalable, and the roadmap points toward a 1-watt version as the next major milestone. At 1 watt, the range of viable applications expands dramatically, covering most IoT sensors, low-power microcontrollers, embedded communication modules, and the standby systems of larger devices.